Pick any positive whole number, and this tiny two-rule machine seems guaranteed to drag it down to 1. Start with 27. It climbs to 82, drops, climbs again, and then absolutely loses its mind. Watch the yellow dot. It passes 100, 1,000, 10,000, and eventually reaches 9,232 before crashing all the way back to 1. Every positive starting number anyone has checked eventually comes home. Trillions upon trillions of cases. Still, nobody can prove they all do. That sentence sounds fake. We have 2 instructions, whole numbers, and no hidden calculus lurking under the rug. Yet this thing has resisted mathematicians for decades. The rules are almost insulting. If the number is even, cut it in half. If it's odd, triple it and add 1. Then repeat. That's the entire machine. I got suspicious the first time I saw this because it has the exact energy of a puzzle where somebody forgot to mention a third rule. They didn't. So keep your eye on 27 as its path becomes this ridiculous mountain range. The question isn't whether 27 returns. We can watch it return. The question is why every possible yellow dot should return, including the infinitely many dots we can never test. And to see why that little gap is so vicious, we need to give the machine somewhere to live. That mountain came from a map you can draw with arrows. Put the positive integers in rows. Every number gets exactly 1 outgoing arrow because the rule never gives you a choice. 8 points to 4, 4 to 2, 2 to 1. 1 goes to 4, so down at the bottom we get the loop 1, 4, 2, 1. That's what reaching 1 really means, entering this tiny carousel forever. Now add 6. 6 goes to 3, 3 jumps to 10, then 5, then 16, and eventually joins the same loop. More numbers feed in, forming branches above branches, like a river system flowing backward. Here's the first little trap. The picture makes the conjecture feel obvious because every branch we draw connects to the bottom, but we're only drawing numbers whose stories we already followed. Somewhere beyond the edge, one arrow path could climb forever, or a separate loop could be hiding, disconnected from the 1, 4, 2 carousel. Those are the only 2 ways Collatz can fail: an escape to infinity or another cycle. Simple options, horrible to eliminate. And there is a strange detail in the arrows that explains why the tree grows so unevenly. Every even number has an obvious predecessor, twice itself. Odd predecessors are picky. To find them, we have to reverse the odd rule, and suddenly divisibility starts deciding who gets a parent. Reverse arrows are picky because an odd step always creates an even number. Triple an odd number, add 1, and you cannot avoid evenness. So the machine immediately earns at least 1 division by 2. We can bundle those moves together. For an odd number n, calculate 3n plus 1, then keep dividing by 2 until the result is odd again. This lets us watch only the odd numbers, which removes a lot of visual stuttering. 27 goes to 41, then 62. Wait, no. This is exactly where I got it wrong the first time. 3 times 27 plus 1 is 82, and removing one factor of 2 gives 41. Then 41 produces 124, which contains 2 factors of 2, so it lands on 31. The odd-only path begins 27, 41, 31, 47, 71, 107, mostly upward. Then 107 creates 322, loses 1, 2, and becomes 161, still upward. Eventually, a step contains a whole stack of 2s, and the number drops hard. This compressed version exposes the real contest. Multiplication by 3 pushes upward, while unpredictable powers of 2 pull downward. If those powers behaved like clean random coin flips, we could estimate who wins, and the estimate is surprisingly comforting. The awkward part, naturally, is that these powers come from the number itself. The coin is attached to the thing we're betting on. The comforting estimate starts with the parity. Among ordinary integers, about half are even. After an odd Collatz move, the result is definitely even. Roughly half the time it has exactly 1 factor of 2. A quarter of the time it has 2 or more. An eighth of the time, 3 or more. So the number of divisions behaves heuristically like repeated coin flips until the first odd result appears. The average stack has 2 divisions. That makes a typical compressed odd step look like multiplication by 3, followed by division by 4, 3/4, downward. On a logarithmic scale, the average drift is -2, which is the version mathematicians actually trust more. Draw enough imaginary steps, and the path resembles a random walk with a slight downhill tilt. This is the first big reason people believe the conjecture. The machine appears biased towards smaller numbers, but a downhill bias doesn't say every walker comes home. A person can flip a coin and get 50 heads in a row. Rare runs exist, and Collatz gives us infinitely many starting points where a rare run could begin. Worse, these parity outcomes aren't independent coin flips. Once you choose N, its entire future is fixed. No randomness enters the machine at all. We borrowed randomness because the residues look mixed. Useful intuition, definitely not a proof. So how long can the machine imitate a streak of terrible luck? For 27, the bad streak lasts long enough to make the downhill story look embarrassing. It needs 111 ordinary steps to reach 1. Before that happens, it rises above every number from 28 through 9,231. If you're watching only the beginning, you would reasonably guess this thing has escaped. Let's plot height vertically and time horizontally again, but color each segment by the rule. Pink means an odd number triggered 3n plus 1. Blue means division by 2. The path keeps making sharp pink jumps, then leaking height through blue staircases. Near the peak, 4,615 becomes 13,846, then 6,123, then 20,170. Careful. 9,232 is the highest value in the full trajectory, while compressed views can make nearby landmarks look different depending on what they omit. Collatz is full of tiny bookkeeping ambushes. Eventually, a deep blue cascade wins, and the whole tower collapses into the familiar loop. Now define the stopping time. How many steps until a starting number first falls below itself? 27 waits 96 steps for that modest achievement. It doesn't even need to reach 1. It just needs to see 26 or lower. This suggests a tempting proof strategy. Show that every number eventually reaches something smaller. Then repeat the argument, descending until 1. Beautiful. One missing piece, proving that first drop for every number. If every number reached a smaller number, strong induction would finish the job almost immediately. Assume all positive integers below n eventually reach 1. Follow n until it dips below n. The assumption takes over and done. This is so clean that it has probably generated several million fake proofs, including one I nearly talked myself into. The problem is hidden inside the phrase, follow n until. We don't know that moment exists. Saying the path should eventually dip because division happens often is the same heuristic wearing a fake mustache. Ordinary induction also struggles because the rule points both ways in size. Even n goes to n over 2, which is lovely. Odd n goes to 3n plus 1, which is larger than n, and outside the assumed range. You can try grouping numbers by congruence classes. Some classes fall quickly. Numbers congruent to 1 modulo 4 take an odd step, and then at least 2 halvings, giving roughly 3n over 4. Great. Numbers congruent to 3 modulo 4 get only 1 guaranteed halving and may rise to roughly 3n over 2. Split those again, modulo 8, 1632. More classes become manageable, while a stubborn residue class keeps slipping through. Every finite analysis leaves some longer parity pattern unresolved. The proof seems to demand control over arbitrarily long patterns. Conveniently, we can manufacture any finite pattern we want. That sounds powerful. It also reveals the trap. Any finite pattern of odd and even steps can be encoded by choosing the right starting number, modulo a power of 2. Want the next 5 states to have parities, odd, odd, even, odd, even. There is a residue class that does exactly that. Extend the requested pattern, and the modulus grows. This works because parity information can be solved backward 1 bit at a time. So those long upward-looking streaks aren't hypothetical accidents. For every finite length, some starting numbers realize them. Notice the escape hatch in that sentence, finite. We can force a path to behave badly for 1,000,000 steps without producing a path that behaves badly forever. Still, it explains why checking more cases never turns into a proof. A computer verifies a gigantic finite forest. Right beyond its boundary are numbers, whose opening moves can imitate whichever unresolved pattern we care to prescribe. The memeable picture here is a binary tree of possible parity strings. Each left edge is even, each right edge is odd. A starting residue chooses a route through the first k levels. Collatz fills every finite depth with valid roots, although positive integers do not necessarily realize every infinite root. That last distinction is tiny on the page and enormous in the proof. Finite control does not automatically pass to infinity. Analysis has a whole collection of theorems for crossing that gap. None fits this machine cleanly, so computation can push the boundary absurdly far. What does that actually buy us? Computation buys certainty for every starting value inside the checked range, and that is real mathematical evidence. A verification program doesn't need to follow each path all the way to 1 independently. It starts at n and stops as soon as the trajectory falls below n, because smaller starts have already been certified. It can also cache known tails, skip predictable divisions, and process residue classes in batches. This turns an impossible amount of repeated work into a merely outrageous amount. Researchers have verified the conjecture across enormous ranges, far beyond anything a person could inspect. The exact frontier keeps moving as implementations and published checks improve, so I'm avoiding tattooing one giant bound onto the screen. Future me would immediately regret it, yet any finite frontier has the same logical shape. Put a wall after the largest checked number. The conjecture asks about every integer to the right of that wall too. There are infinitely many. Moving the wall a trillion times farther barely changes that fact. Computation can also hunt for cycles. If a cycle exists, multiplying the odd step equations around the loop forces powers of 2 and powers of 3 into a very tight numerical relationship. That lets us rule out broad classes of small or simple cycles. Any hidden loop would have to be enormous and exquisitely balanced, which raises the next question: what would such a loop actually need to look like? Suppose a cycle contains odd steps and b total divisions by 2. Ignoring the added ones for a moment, returning to the starting scale requires 3 to the a to sit very close to 2 to the b. If 3 to the a is much larger, the loop grows. If it's much smaller, it shrinks. The plus ones prevent exact cancellation and make the constraints even sharper. This becomes a problem about rational approximations to log base 2 of 3. The cycle's counts would need an uncanny numerical fit. We already know one positive cycle, 1, 4, 2. Under the odd-only shortcut, that's just 1 returning to 1. Searches and theoretical bounds force any other cycle, if it exists, to contain a huge number of steps, huge enough that drawing the nodes individually would be a hostile act toward the animator. But ruling out all cycle lengths means controlling infinitely many near matches between powers of 2 and powers of 3 while also tracking those accumulated plus 1 terms. Number theory can prove strong lower bounds. It doesn't close the door. And even if somebody sealed every possible cycle tomorrow, an orbit could still wander upward forever without repeating. Integers are discrete, so a bounded orbit must eventually repeat. An unbounded orbit has unlimited room to keep inventing new values. We therefore need to understand escape as well as repetition. The random walk model says escape should be fantastically unlikely. Mathematics now has results that make that belief much more precise, though their use of the word almost deserves a warning label. For almost all starting numbers, we can prove behavior that strongly resembles the downhill heuristic. Results going back decades show that almost every integer, in a precise density sense, eventually reaches a value smaller than where it started. More recently, Terence Tao proved a much stronger statement. For almost all starting values, the orbit eventually drops below any function that tends to infinity, no matter how slowly, using logarithmic density. That sentence takes a second. Choose a painfully slow-growing threshold. Tao's result says almost every starting number eventually gets underneath it. This is extraordinary progress. It still leaves the conjecture alive because almost all is allowed to exclude infinitely many numbers. The exceptional set can have density 0 and still contain a counterexample. Squares have density 0 among the integers. Powers of 2 have density 0. Both sets go on forever. Collatz needs every single start. One rebellious integer ruins the statement. There's another subtlety. Different notions of density weigh integers differently, and Tao's theorem uses one suited to multiplicative behavior. Honestly, the notation around these density statements gets spiky fast, and I'm sorry on behalf of mathematicians. The useful picture is simple. As our window expands, the proportion of suspected exceptions becomes vanishingly thin. Vanishingly thin doesn't mean empty. Can a proof somehow squeeze thin all the way down to none? Squeezing the exceptions to none requires information. The usual averages throw away. Collatz mixes two kinds of structure that are individually friendly and jointly awful. Parity lives in powers of 2. The odd rule multiplies by 3. Repeated steps create expressions involving both powers. plus a trail of accumulated constants. If we fix a finite parity pattern, we can write the final value exactly as 3 to some power times n, plus an offset, all divided by a power of 2. That's useful. The offset depends on where every odd step occurred. Make the pattern longer, and the expression remembers more history. Modular arithmetic can control any fixed window. The conjecture asks for an unbounded window whose length depends on n, in ways we do not understand. Averages smooth over the rare residue classes. Induction trips when values rise. Cycle arguments miss escape. Computation ends at a wall. Each tool grabs one part of the machine, and the counterexample, if one exists, can keep moving into the part that tool ignores. This is why the problem feels weirdly alive. Every time we corner it, it changes scale. Small numbers become huge trajectories. Finite patterns become an infinite question. Near certainty becomes a single possible exception. There is also a darker clue. Slightly more general machines built from rules like these can simulate arbitrary computation. Once that happens, predicting whether an orbit stops can become logically undecidable. How close is Collatz to that cliff? Generalized Collatz systems can encode computation. John Conway constructed related arithmetic rules. We're asking whether every orbit eventually reaches a certain state is undecidable. No universal algorithm can correctly answer all instances. The rough magic is that residue classes act like program states. Depending on a number's remainder, the machine applies a different multiplication and addition, updating both the stored data and the next state. An integer becomes a whole computer squeezed into prime factors. This does not prove the original 3n plus 1 problem is undecidable. That distinction matters a lot. Our machine has one extremely specific pair of rules, and extra freedom is exactly what makes the general constructions programmable. Still, the result kills the comforting belief that every elementary-looking iteration must have an elementary proof. Tiny arithmetic rules can hide arbitrarily complicated behavior. Collatz may sit on the tame side of the boundary and merely require one brilliant invariant nobody has found, or its trajectories may simulate enough complexity that our current methods are fundamentally mismatched. People have proposed countless quantities meant to decrease: size, weighted parity, residue scores, combinations of logarithms. The orbit usually finds a way to increase them somewhere. A successful proof may need a global object that measures an entire family of trajectories at once, or a new bridge from almost every number to every number. What would count as an actual finish? An actual finish needs to eliminate both monsters, no non-trivial cycle, and no orbit escaping to infinity. One route would prove every starting value eventually falls below itself. Induction would handle the rest. Another could discover a quantity that decreases across blocks of variable length, with no exceptional residue class left behind. A third might upgrade density results by showing any hypothetical exception forces so many nearby exceptions that density zero becomes impossible. That idea is especially tempting. Make one rebel contagious, then use the fact that almost everyone behaves. Nobody currently knows how to make the contagion strong enough. So here is the full picture I keep coming back to. At the bottom sits the tiny loop 142. Above it, verified trajectories form an enormous branching basin. Probability points downward. Computation pushes the known basin farther out. Number theory fences hidden cycles into absurd territory. Density theorems squeeze possible escapees into thinner sets, and somewhere beyond every drawn boundary, there may be one yellow dot refusing to come home. We have overwhelming evidence and several deep partial victories. The last step demands a statement with the word every in it. That word is doing almost all the damage. Here's the thing that still bugs me. If there is a counterexample, its first few million moves can look completely ordinary. It can fall, rise, brush against familiar territory, and then leave. So what feature could possibly reveal it before it escapes?